In this video, we will discuss about the elementary theory of an ideal transformer. So, what is the basic meaning of an ideal? Suppose we consider a system over here. It has two terminals. One terminal is input and the other terminal is output. Right now, we are not considering this third terminal. Suppose we are giving 100% input to this system and we are getting 100% output. So then this system will called as an ideal system. Okay. If suppose the third terminal is added and we are giving 100% input to a system and we are getting 98% of the output, but 2% is going to be lost. At that time, we'll not call it as an ideal system. It is what? It is somewhat practical system. Okay. So why we are considering this ideal transformer? So to have an analysis of a transformer without assuming or without considering it a practical, just we want to establish a basic theory of a transformer. Okay, so basically what is a ideal transformer? An ideal transformer is what? Which is having, number one, which is having no losses. No losses means an ideal transformer has, number one, no losses, that is winding losses, or winding has no ohmic resistance. Okay, means if we say what is an ideal transformer, means ideal transformer is that which is having no ohmic losses. Okay, second is what? It is having no leakage magnetic, okay, or we can say no magnetic leakage is there, means there is no leakage flux, that is there is no leakage flux. All the flux are useful flux. No leakage flux is there. It means that is it has no core losses. Okay. So it means from these two we can say that an ideal transformer is that which has no I square R losses, number one, and no magnetizing or core losses. Okay, this is what about the basic property of a ideal transformer. Suppose we are considering a transformer. This is what? This is a core. This is one of the leg and the other leg. On one of the leg there is a winding and this winding is connected to a supply, and this is another winding which is kept open. So at here means at secondary winding the no load is connected. Okay, here it is what? It is a alternating source connected to the primary winding. Let it be V1. Okay, so what will happen? This is basically a ideal transformer. Ideal transformer means we are not considering any sort of resistance in the primary winding and no sort of resistance in the secondary winding. So it means it is lossless or loss free. Okay, so we can say the winding is loss free and the core is loss free. Both the things, windings are loss free. Loss free is what? Windings are loss free and core is also loss free. So what will happen at this time when we are considering it as a loss free? This will purely act as an inductive circuit. This primary circuit will purely act as a inductive circuit. So what will happen? What will happen when the primary winding is connected to the AC voltage source? Because of the potential difference, there is a flow of current in the primary winding, and this winding, as the load is not connected, there is a flow of a magnetizing current which is denoted by I mu in the winding, and this magnetizing current will establish a flux phi in the winding or the core, and this flux will link with the core and establish or induce a self induced EMF given by E1, which is opposing, by which it is caused. This is what the Lenz's law. Okay, it means V1 is equal to E1, but it is opposing. It is in opposition. Okay, now what will happen? This flux will flow through the core and link with the secondary winding. This here we are not considering any sort of leakage flux, because this is what we considered, that there is no leakage flux, means it has no core losses. Okay, the whole flux is linked with this primary winding. So the nature of the flux is what? It is keep on changing, and the conductors, that is the winding, these are stationary. So there is a mutual induced EMF which is given as E2. Okay, this E1 is what? E1 is self-induced EMF, whereas E2 is what? It is a mutual induced EMF. There is a difference between these two words. Self is what? Means when there is a flow of current in the winding, the flux is established and E1 is induced. Here in this winding there is no flow of current, but what will happen? This flux is going to be linked with the secondary winding, so there is a establishment or another E2 EMF will induce, which is because of the mutual induction, okay, or the mutual coupling between the primary flux and the secondary flux, okay, secondary winding flux. So this is what the E2 is. It means right now it is purely inductive. So what will happen? The waveform would be, it is what? It is x-axis, this is y-axis. Okay, we are considering it even here. So what will happen? So here what is the concept? This phi is because of this current I. This phi is directly proportional to the I mu. Okay, so both are in same phase. Both are in same phase. Okay, means if this is I, then this is phi, means both are in same phase. Now what? Suppose V1 is what? It is a applied voltage. Because of this V1 there is a flow of I current I mu, and because of this I, flux phi is established, and because of this flux E1 is induced in the primary circuit. This is what, these are the components or the parameters of the primary circuit. So V and I is having a inductive nature or the lagging. Okay, suppose this is what? This is V1. This is V1. So what will happen to the I? It is a purely inductive. It means the I current will lag by an angle 90 degree. So this is what? I. This is I, the current, or we can say I mu. Now as I mu produces this flux phi, both are in same phase, it means both are in same phase, means this is what the flux phi, this dotted line, Okay, this is what the flux phi. Now here V1 is equal to V2. V1 is equal to E1. Here V1 is equal to E1, but both are in opposition. So what will happen? This is V1. It will have same magnitude, but in opposite direction. So this is what E1. Okay. Similarly, because of this E1 and flux phi, when flux phi is mutually coupled with E2, this secondary winding, what will happen? There is a production or induced EMF E2. It means E1 is equal to E2 and both are in same phase. Therefore, both are in same phase. Therefore, this waveform, this red waveform, this is what both are in same phase. This is what E2, this is E2. As I have considered here E1 is equal to E2, but here we are I am showing the magnitude of E1 and E2 is different, so we are not going to consider it as equal to, but both are in same phase. Okay, so this is what basically the wave shape for the all quantities which are associated with an ideal transformer. Now next point is what phasor diagram of an ideal transformer. Now I and phi both are in what? Both are in same phase. So we are considering I on the x-axis. Now the relation between I, this is what I and this is what phi. Both are in same phase. Now the relation between I and V1 is what? It is the inductor circuit. Means for an inductor we know that current, this is what V and this is I. For an inductor we know that current lags by an angle phi, or for an ideal inductor or the pure inductor we know that this is V, this is I, it is making an angle 90 degrees. This is what the ideal inductor or the pure inductor. This is for ideal or pure inductor. Okay, so we are not going to consider this because this is for the practical inductor or the means the real inductors. We are considering the ideal. So this is what, if we change the orientation or we rotate it by 90 degrees, so what will happen? This is what I, and this will be the this is what I, and this will be the V, and it is having an angle 90. If we are going to change the orientation of this vector by 90 degree, so the same thing we are going to keep here. So this is what I, this is V. So what will happen? There is a lag between V1 and I. I what? This current I mu. Okay, as we can say that this is I, the I mu. Why? Because the load is not connected, so we can consider it here as a I mu, and we are not considering the losses, so I is equal to I mu. So right now we are considering it here as a I. So it is having an angle what? 90 degree. Now what is the relation we had? V, when we connecting the primary voltage V1, there is a current flow I1 or I. Because of this, flux phi is produced, and then there is a E1, and this E1 and V1 both are equal but in opposite. So both are equal but in opposite. It means this is what E1 is. Okay, both are equal in magnitude, but they are in opposite phase. Then what will happen? This flux phi linking with this secondary winding and producing E2. And previously what we have considered, In this waveform, we consider that E2 is somewhat less than even. Okay, E2 is less than even, but both are in same phase. Phase is what? It is same. So what will happen? This is what? E2, which is less than even, but both are in same phase. It is what? It is a 90-degree angle, and this is what? The 90-degree angle. This is what the complete phasor of an ideal transformer. Okay, thank you.